Okay, so hey guys, we're going to go ahead and go over day 2 notes today, Lewis structures for ionic compounds. And actually, I'm only going to work on the sample problems because a lot of this, especially the first page was all review from last semester. Okay, so you should already know a majority of this. You should already know all of this. Okay, so the second page has to do with some of the rules you need to know. So this page is completely new. So hopefully you were paying attention in class. And I am just going to go over the sample problems with you guys today. Okay, so our first sample problem was H2O. So I'm just going to show you the easy way to do it. I know Miss Williams and even Mr. Lawrence teaches it differently. So I'm going to try my best to go over both ways, but I'm going to go ahead and show you my way first. Okay, so if you recall from our notes that one of the rules for drawing a Lewis dot structure is that your first element is, or your first atom is always going to be the first element in the formula. So in this case, it's hydrogen, but you guys should know that one of our rules is that if hydrogen cannot be the central atom. So because hydrogen can't be the central atom, we're going to have to use the next atom, which is, or our next element rather, which is oxygen. So oxygen is going to be our central atom. Okay, so let me just zoom in just a little more. Okay, so that would mean that H, or hydrogen, is going to be right next to it. Okay, remember one of our other rules. Okay, it has to look symmetrical. Okay, so now that we know what our elements are, we're going to go ahead and put our valence electrons in here too. So if you guys remember, hydrogen has 1 valence electron. Okay, so 1 valence electron for each of them. And then oxygen has 6 valence electrons. Okay, so hopefully by this time you guys know where to look for valence electrons. Okay, zoom in some more because there's no need for a let space. Okay, so now that we have our individual atoms, I have both my hydrogens and I have my oxygen. I left out one more valence electron. Okay, so hydrogen, each of them have 1 valence electron. Oxygen has a total of 6. So remember, covalent bonding, they are going to be sharing electrons. Now our rule, the bus seat rule, well, we have 2 empty seats right here. So that means these our hydrogen electrons can go ahead and take that seat that's left on the bus. So hydrogen's valence electron is going to pair up with this valence electron, and this valence electron is going to pair up with oxygen. Okay, so these two are sharing, and then those two are sharing seats. So when we rewrite our formula, we're going to have hydrogen and hydrogen, and then an oxygen in the center. Okay, and we're going to look at what we drew above. So between this hydrogen and this oxygen, how many bonds did we create, or how many valence electrons are being shared? Well, we have 1 bond. Okay, so between this hydrogen and this oxygen, we created 1 bond. Okay, and between our second hydrogen and oxygen, well, they created 1 bond as well. So we'll have another bond right there. Okay, now we need to take a look at the number of lone pairs we have for any of our elements. And remember, lone pairs are our electrons that are not being shared. So if you take a look, these electrons, 1, 2, 3, 4 valence electrons for oxygen are not being shared. So we need to make sure that they are still included in our final structure. Okay, so when we check our work, hydrogen has 1, 2 electrons that's being shared with the both of them. Same thing for this hydrogen. And then oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. Okay, so our final structure for water, for H2O, is this structure right here. So what I was telling my students in my class is that on your quiz, this is what I expect to see. This is going to be your first answer, and then technically your second answer right here, your final answer here. Okay, so just like your homework, on your homework, your first step is to show me this work right here, and then the second box is this right here, your final molecular structure. Okay, so I'm also going to go ahead and show you the way that the other teachers might be showing you. So the way they do it is you are always going to start off with how many valence electrons do you have compared to how many valence electrons you need. Okay, so in case of water, okay, we have hydrogen and we have oxygen, okay, and we have 2 hydrogens. Don't forget that. So we have a total of 2 valence electrons for hydrogen. Remember, they have 1 valence electron, okay, but we have 2 hydrogens, so we have a total of 2. And then oxygen, we only have 1 oxygen, but oxygen has 1, 2, 3, 4, 5, 6 valence electrons. Okay, so that is a total of 8 valence electrons that we have. Now, how many valence electrons do we need? Well, remember, if we have 2 hydrogens, and for hydrogen to be happy, it needs a total of 4, or I'm sorry, each hydrogen needs a total of 2. So that means, oh my goodness, I have tape on my finger now. Okay, so that would mean that we need a total of 4 valence electrons, okay, for 2 hydrogens to be happy. Okay, so oxygen, we know that oxygen needs to have a total of 8. It does follow the octet rule, so oxygen needs to have 8. So when we add them together, 8 plus 4 is 12 total. So if we need 12 and we only have 8, then that means 4 electrons are going to be shared between water. Okay, so because that's 4 valence electrons being shared, then that means we have 2 bonds for our central atom. Okay, and when we check our work, well, we already did it. Okay, do we have 2 bonds being shared by our central atom? And we do. We have 2 bonds, 1 and 2. Okay, so remember, your 2 bonds always refers to your central atom. How many bonds does your central atom have? Okay, so if you like the very simple, straight to the point way, it's tedious, yes, because of all the dots, but it's very straightforward. Okay, but if you're more of a math person and you prefer to do it the math way, you can do it this way also. Okay, so let's go ahead and take a look at our next sample problem. We have carbon dioxide. Okay, so we have carbon dioxide. So again, I'm going to show you both ways to solve for this. So remember, when drawing our Lewis structure, our first element is going to be our central atom. Not unless it's hydrogen, then it would be the second one. Okay, but this is not hydrogen, so our our central atom is going to be carbon. Okay, so carbon is going to be our central atom. Okay, so that would mean oxygen is going to be the element that's on either side of carbon. Okay, and I'm going to go ahead and draw my Lewis dot structure. So on your periodic table, oxygen has 6 valence electrons. 1, 2, 3, 4, 5, and then 6. So 1, 2, 3, 4, 5, and then 6. Okay, and then carbon, again, on your periodic table, we only have 1, 2, 3, and 4. Okay, so now that we have our individual elements with their Lewis structures or their valence electrons, we can now go ahead and connect our single valence electrons. So these two right here, okay, these two can create a pair. Okay, and then these two can also create a pair. Okay, think of this like a dating game. Okay, if you have a seat on the bus that's already filled, you leave that couple alone. Okay, but these valence electrons, they're single, and they don't want to be alone for forever, right? They don't want to be forever alone. So they're going to go ahead and pair up with the valence electrons from the other element, right? So those two are going to pair up, these two are going to pair up. And then on this side, you also have these two, and I know this is going to be a crazy long circle, but these two are also going to pair up. Okay, so again, we have to rewrite our final structure. So we have oxygen, carbon, and another oxygen, right? Now, between this oxygen and carbon, how many bonds did we create between them? Well, we have this circle and this circle, so that means we created 2 bonds between our first oxygen. Now for our second oxygen, it would be the same thing. We created 1 and 2 bonds, so 2 bonds right there. Okay, and then lastly, we have to go back and make sure, well, do we have any lone pairs? Do we have anyone or any couples in the group? And we do. We have 1, 2, 3, 4 lone pairs, okay? So does it really matter where you put these lone pairs? No, I can put them up top, or I can even put them right here on the sides. But remember, nature likes symmetry, so I'm just going to keep them the same just like that. Okay, so that is for carbon dioxide. Now, let's go ahead and take a look at the math way. Okay, so we have, valence electrons that we have versus the valence electrons that we need. Okay, so we have carbon and we have oxygen. Okay, and we have 2 oxygens. Okay, so carbon has 4 valence electrons and oxygen has 6 valence electrons, but we have 2 of them. So that's going to be 6 times 2 is 12, which gives us a total of 16. Now, how many do we need? Carbon needs 8 to be happy. For a complete valence electron, it needs 8. It likes that octet rule. Now, it's going to be the same thing for oxygen. Oxygen also needs to have 8, but we have 2 of them, so that is 16. Okay, so let me see. So when we add that all together, okay, 16 plus 8, sorry guys. Okay, 16 plus 8 is 24. Okay, so that's how many we need. So if we subtract those two numbers, we need 24, but we only have 16. Well, 24 minus 16 is 8 valence electrons shared. Okay, so if we have 8 valence electrons shared, well, that's equivalent to 4 bonds being shared. Okay, so that means your central atom is going to have 4 bonds. And we can verify that by our final structure. Carbon, our central atom, does in fact have 4 bonds. Okay, but the only reason why I don't like doing it the math way is that you don't really know where the bonds go. Okay, you kind of have to figure it out for yourself. Okay, 2 on this side, 2 on this side. Well, that's not always the case, which we'll see in just a little bit. Okay, so that's it for carbon dioxide. Okay, we're going to go ahead and move on to the next example, okay, which we have here. Okay, HCP, so hydrogen, carbon, and phosphorus. Now remember, hydrogen cannot be our central atom, so that would mean we have to use the second element as our central atom. So that means we are going to have hydrogen on one side, and I'm going to go ahead and draw my valence electrons too. Okay, hydrogen has 1 valence electron. Carbon is our central atom, and it has 4 valence electrons. Okay, and then lastly we have phosphorus. So phosphorus has 1, 2, 3, 4, and 5. Okay, so those are our elements with their valence electrons. So now that we have that, we can go ahead and start pairing up our single electrons that are going to be shared. Okay, so hydrogen has a single one, so it's going to create a pair with that one right there. Okay, now things are going to get crazy with all these circles. So there's one right here that can be a pair. These two can create a pair. And then lastly, this is going to be a long stretch, but these two can also create a pair. Okay, and then we have a little lone pair or our couple that does not want to be disturbed, but all these single people are hooking up, right? They're creating a pair. They're creating a couple. Okay, so for our final structure, we can just rewrite our 3 elements: hydrogen, carbon, and phosphorus. Now, how many bonds did we create between hydrogen and carbon? Well, it looks like the only ones they shared is this one right here, so just 1 bond. Okay, between carbon and phosphorus, well, we have 1, 2, 3 circles or 3 bonds that we created between them. Okay, so those are all our bonds. And then lastly, don't forget about your lone pairs. Okay, so phosphorus is the only one that had a lone pair. So we're just going to put that anywhere on phosphorus. We could have put it on top, we can put it on bottom. It doesn't really matter. Okay, so this is our final product for HCP. Okay, so now the math way. Let's go ahead and take a look. Okay, so the math way, valence electrons that we have versus the valence electrons that we need. Okay, so we have 1 hydrogen, okay, which has 1 valence electron. We have 1 carbon that has 4 valence electrons. And then we also have a phosphorus that has 5 valence electrons. Okay, now how many do we need? Hydrogen needs 2 to have a full valence shell. Carbon needs 8. And then phosphorus also needs 8. So when we add all that up, 5 plus 4 plus 1, that's 10 valence electrons that we have. And then how many valence electrons do we need? 8 plus 8 is 16, plus another 2 is 18. So if we need 18, but we only have 10, then that means that 8 valence electrons are going to be shared. Okay, so 8 valence electrons is equal to 4 bonds. Okay, so again, this is what I don't like about the math way. You don't really know where those 4 bonds are going to go. You kind of just have to be educated, and you should know that hydrogen, that one of your bonds should go between hydrogen and carbon, because hydrogen only needs those 2 electrons to be happy. Okay, now the other 3 bonds are going to go between carbon and phosphorus, so that way both of them can also have their 8 valence electrons. Okay, so again, whichever method you prefer, for my class, that's fine with me, but if you are in another class, just be careful, because the way they grade their quizzes might be different. They might expect this versus this right here. Okay, now let's go ahead and go over our last example. Okay, we have N2, a diatomic. Okay, now we only have 1 element, so can we really say, is there a central atom? No, there is no central atom because you only have 2 nitrogens. So nitrogen and nitrogen. Okay, nitrogen has a valence electron. It has 5 valence electrons. So 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. Okay, I had one of my students ask me earlier, Miss Breeze, well, how do you know where to put your single pair of electrons to make it easier to bond? Well, I always tell them, try your best to put your single valence electrons close to the center of the element. So, a good example, well, I don't really have one. Well, I'll tell you guys later. Okay, but this could be an example right here. I put my single electron, my single valence electrons, all next to each other because I already know that my lone pairs aren't going to be shared at all. So that's why I put them on the outsides. Okay, and then on the insides, I put my single electrons because I know when it's time to connect them, all I have to do is just circle them because they're right next to each other. Okay, because if you had done it the other way, so if you had N and N, and you put 1, 2, 3, 4, and 5, 1, 2, 3, 4, and 5, well, you'll have one here, one here, but then for these 2 on the outside, you're going to have to go a long ways to create that. So that's why you usually want to keep your single electrons towards the center. Okay, you want them pointed closer to the central atom as much as possible. Okay, so when you finally create your Lewis dot structure, well, how many bonds did we create between the 2 nitrogens? Well, that's 1, 2, and 3. We created 3 separate bonds, and then don't forget about your lone pairs. Okay, we have 2 lone pairs, or a total of 4 valence electrons. Okay, and that's it. So the math way, really quickly, we have valence electrons that we have versus the valence electrons that we need. So we have nitrogen, we have 2 of them, we have 2 nitrogens, and they both have 5 valence electrons, so that's 10. Okay, again, we have 2 nitrogens, but we need 8 valence electrons for them to be happy. So, so we need 8 valence electrons for them to be happy. So 8 times 2, that's 16. So 16 minus 10 means that there are 6 valence electrons that are going to be shared. So that's equivalent to, not 4, 3 bonds. Okay, because 6 divided by 2, that's going to be 3 bonds. Okay, which is what we have up top, right? So this is the only way that doing the math way could be easy when you only have 2 atoms or 2 elements. Okay, so you don't really have a central element, so you know that those 3 bonds are going to be shared between these 2 nitrogens, and then you would have 2 lone pairs. Okay, so that concludes our notes for today, or our sample problems. If you guys have any questions, please ask. Today's notes was probably the most important day, because if you do not know how to do this stuff and how to create a Lewis structure for a molecule, then you are going to get lost for this whole unit. Okay, today was probably the most important day. So if you don't know what you're doing, please ask for help. Okay, do not be afraid to ask for help from your teacher. If you're too scared to ask your teacher, come and see me. Okay, you guys have a great day. Good luck with your homework.